Now, I will explain the agenda for this webinar. First, will be the opening from the Master of Ceremony. Second agenda will be the singing of National Anthem and Etika Hymn. Next will be the opening speech from the Chairman of World Class Professor Program, Dr. Engineering Yunita Triana S.Si M.Si, an opening speech from Vice Rector of ETK, Professor Dr. Nurul Widyastuti, PhD, followed by the first photo shoot session. And after that, we will go into the main agenda, the discussion session moderated by Ms. Lia Amalia with our 5 speakers, and we will close the webinar with handing over certificates. And last, photo shoot session so we can still see the beautiful faces of all the participants. So I hope everyone will be staying until the end of this webinar. But before we get started, we'll begin with prayers to God Almighty to ensure the success and benefits of this event. You may pray according to your beliefs. Let's pray. Amin. And now it is time to sing Indonesian anthem, Indonesia Raya, and hymn of ETK. All attendees, to make this webinar more exciting, I would like to present to you traditional dance of Borneo, performed by the student of Materials and Metallurgical Engineering. Please enjoy. Okay, give applause to the performance of Borneo dance team. All right. Excellencies, ladies and gentlemen, following the next agenda will be the opening speech from the chairman of World Class Professor, the Honorable Dr. Engineering Yunita Triana S.Si MSD. Dr. Yunita, the time is yours.
Yeah, is everybody can hear my voice? Is it okay? Mr. Vikan, can you hear my voice?
Yes, it is loud and clear.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Your Honorable the Vice Rector of ITK, Professor Nurul Widyastuti, PhD. Good morning, Professor Nurul. And the keynote speaker, Professor Dr. Yasuaki Einaga from Keio University. Good morning, Professor Einaga. Good morning, invited speaker, Associate Professor Takeshi Kondo from Tokyo University of Science, Professor Ivandini from University of Indonesia, Mrs. Prastika, PhD from University of Erlangga, and Mr. Irham, PhD from University of Pajajaran. The Committee of World Class Professor Second Series, and all the audiences today. First of all, allow me to introduce myself. My name is Yunita Triana. I am the chairman of World Class Professor Second Series for the event of international webinar with the topic Promising Materials of Boron Doped Diamonds, Electrode to Electrochemical Sensors. As we know together that carbon-based semiconductor material have attracted so much attention in the last 10 years, such as carbon nanotube, graphene and its derivatives, doped carbon, and then glassy carbon, and also boron doped diamond electrodes or BDD. This is because carbon material is inexpensive, abundant in nature, and easy to produce, and also have high durability. To support the development of BDD research in ITK, we need some special event, academic event, from the many speakers who expert in the BDD research. So today they will share their best experience, they will share their best knowledges about the BDD research area, research field, in many applications. I hope everybody can enjoy today's event. And thank you for your today's enthusiasm. And I know that all speakers today are very busy, but they have time for us. So I hope that lecturers and students can get some valuable knowledge from them. And thank you very much for your support and attention. I hope you can enjoy this event. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Engineering Yunita, for the speech. And we also invite to the stage the Honorable Professor Dr. Nurul Widyastuti, PhD, the Vice Rector of Institute Teknologi Kalimantan, for the opening speech. To the Honorable Professor Dr. Nurul Widyastuti, PhD, the time is yours.
Thank you, Mr. Vikan. Very good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Honorable speakers, Professor Yasuaki Einaga from Keio University, Japan, Professor Ivandini from Universitas Indonesia, Dr. Ihram from Universitas Pajajaran, Dr. Prastika Krisma from Universitas Erlangga, and distinguished academic members of Institute Teknologi Kalimantan. It gives me great pleasure to welcome all of you in this event, the World Class Professor Meeting Series that today bring up the themes on promising materials of boron doped diamond electrodes to electrochemical sensors. As we know that the education, innovation, and technology have always been a top agenda of the Indonesia governments, which include a substantial increase in research and development resource between education, industries, and society. We do hope that by discussing the topics, we will get insight, new idea, initiate and develop collaboration between us in order to increase the quality of education, research, human resources, and also facilities. Our collaborations will always bring us benefit for both sides, increasing the quality of education and research. And in Institute Teknologi Kalimantan, just to inform to all of you, has developed a strong foothold in energy, smart city, and marine, and also food research. Thus, the research in ITK will focus on the issues. And I think that's related the topic of electrochemical sensors. It exactly has a contribution to the research focus on energy, food research, as well as smart city and marine, since sensor has a huge applications. Besides that, ITK also has 20 study programs, and mostly in the field of science, engineering, and also information technology. To step up our collaboration in education research as well as innovation and technology, ITK has actively worked together with other universities in Indonesia and also other countries, industry as well as government, including the local government. Together, we achieve our dreams. And finally, Bismillahirrahmanirrahim, I open the World Class Professor meeting series in the theme on promising materials of boron, doped diamond electrode to electrochemical sensors. Hope all of you will enjoy the meetings and have benefit from it. Assalamualaikum warahmatullahi wabarakatuh, and I give back to Mr. Fikam.
Thank you very much to the Honorable Professor Dr. Nurul Widyastuti for the speech and the opening. To all attendees, before we go to the main agenda, we would like to do the first photo shoot section. That will be led by the operator. So we humbly ask you to turn your camera on.
Okay, thank you, Mr. Fikam Mubarak. I will taking photo from first page. 1, 2, 3. Okay, thank you. Second page. 1, 2, 3. Thank you. Third page. 1, 2, 3. Yeah. Fourth page. 1, 2, 3. Okay, thank you.
Okay, thank you for your brightest smile. So next, let me introduce you to our moderator today, Mrs. Leah Amalia SDMS. She has several research experiences with a demonstrated history of working with several higher education institutions. She is one of the lecturer of materials and metallurgical engineering, and now she is also a PhD candidate from University of Tennessee. Without further ado, please welcome Mrs. Leah Amalia SDMS. Time is yours.
Hello, everyone. Can you hear my voice?
Yes, your voice is clear. Thank you.
Okay. Hi, welcome to the first session of the second World Class Professor series. Now, our first speaker is Professor Yasuaki Einaga from Keio University. And this professor is a highly decorated professor. He was awarded a bunch of awards, such as in 2016, He was awarded with the Ichimura Prize in Science for Distinguished Achievements from the New Technology Development Foundation. And recently, in March 16, 2022, he was awarded with the Scientific Achievement Award from the Electrochemical Society of Japan. He studied his bachelor's, master's, and doctorate degree in the Department of Chemistry in the University of Tokyo, Japan. So today, we're very honored to get a chance to hear his presentation about boron-doped diamond electrodes for electrochemical sensors. So before we provide Professor Einaga with the floor, I will remind everyone that we will have 30 minutes for each session, including the short Q&A session at the end. So yeah, just to keep in mind that we have a pretty short time for each session. Professor Einaga, are you already here?
Yes. Good morning.
Okay. Good morning. Yeah, so I've introduced you. Now the floor is yours. Take it away. Thank you.
Thank you. Oh, can I start?
Yes, go ahead, Professor.
Okay. Okay, sorry.
It's okay.
Can you see?
Yes, we can see it.
Okay. Thank you, Leah, for nice introduction. So thank you very much. So, Selamat pagi, everyone. My name is Einaga from Keio University, Japan. So, first of all, I'd like to say thank you to Dr. Yunita Triana, Nita-san, so for organizing this workshop and giving me a chance to talk here again. Actually, nice to see you again today. Okay, so today's topic is diamond, boron-doped diamond electrode, and today's speaker, all of the speaker is like my family. Yes, so it is like a group meeting of my group meeting, I think. But anyway, maybe some of you already know, listened to my talk before. So today's topic is maybe repeated one. So maybe some of you already know some topic. But anyway, I will introduce again from the beginning our electrochemical application of boron-doped diamond electrode. Okay, just I will talk in 20 minutes to 25 minutes, okay? Okay, I'll start my presentation. Okay, so before coming to my talk of application, so this is a background of boron-doped diamond. You know, diamond is an insulator, but boron doping is important. When the boron is doped into the diamond, the conductivity increases. So when the boron doping level is like this, low concentration, this shows a p-type semiconductor. So this diamond is studied by many people. Insulating diamond and the p-type semiconducting diamond are studied by many people. On the other hand, we are focusing on relatively highly doped diamond, highly boron-doped diamond around this region from 0.1% to 1% BC ratio is like this. This shows metal-like conductivity. So we can use this diamond as an electrode material. This is our research on boron-doped diamond electrode. Okay. So how to prepare boron-doped diamond? There are several methods, but here I'll show our our method is a microwave plasma CVD system like this. So as a carbon source, we are using acetone. This is a liquid boron, a liquid carbon source. And as a boron source, we are using a boron. This is a liquid source of boron. And we can mix these one, and we can control the concentration for carbon and boron. So we can control the conductivity from the insulator to metal-like conductivity. Okay, so by using this chamber, we produce hydrogen plasma by using hydrogen here, and using microwave, we produce hydrogen plasma. Then here we introduce this carbon and boron by bubbling by hydrogen. Then carbon and boron is introduced in this chamber, in this plasma. Then on this substrate, we are normally use silicon substrate. Then on silicon substrate, the boron dot diamond is deposited on this surface. This is a surface SEM image. It is a polycrystalline diamond, boron dot diamond. Okay. So we are using this one as an electrode material. So when we use this boron dot diamond as an electrode material, this shows a very nice electrochemical properties like this. These are the very nice electrochemical properties. So by using these properties, we can use as an electrochemical application. So I will explain in detail later. So anyway, by using these nice properties, we are applying this electrode to many application fields, especially sensor application. So for environmental sensor and biomedical sensor. So actually in these years, we are concentrated on application of sensor. But recently, not only sensor application, but also some other application, like wastewater treatment, ozone water generation, or recently the CO2 carbon dioxide reduction is also the very important subject recently in the world, as you know. So these one also. And also, the important point is fundamental study on diamond electrode. Why diamond electrode is good? Because some of the properties. So we should know the fundamental of this electrode. This is also important. Anyway, today, just I want to show some very small, briefly about the application. Actually, Dr. Plastica will introduce some of her work related to the CO2 carbon dioxide reduction research. But anyway, and this area is actually mainly done by Dr. Ilham also. And anyway, I will introduce very briefly about these two topics. Okay. Okay, now coming back to this electrochemical property of boron dot diamond. So the most important point property is a wide potential window and low background current. This is good for the electrochemical sensor application. Of course, stable diamond, because this is diamond. Diamond is very stable and very stable, and such property is very important for any application. But of course, for sensor, it is also good. Anyway, maybe you, some of you know about electrochemistry well. So in that case, this is well known. Anyway, after normally when we use conventional electrodes such as glassy carbon, gold, and platinum, as you can see, at around 1 point some volt around here, the oxygen evolution starts. On the other hand, when we apply to the negative potential to minus 0 point something, hydrogen evolution start. So this, we say this is a potential window. So normally when we use the conventional electrode, glassy carbon, gold, and platinum, the potential window is always like this. On the other hand, when we use the boron doped diamond electrodes, the potential window is very wide. So it means oxygen evolution is difficult to apply. So you should apply to the high potential, positive potential to produce oxygen, and to negatively, we need to apply to the negative potential to produce hydrogen. So this is a wide potential window. Another one is a low background current. Low background current means around here, as you can see, no current is observed. No, very small current is observed here. But on the other hand, in case of conventional electrode, some small current is observed. This is due to the capacitance of the surface of the electrode. Okay, so this is very good. So the background is very small. So it means that for sensor, this is good. The sensitivity is very nice. Okay, based on these properties, so far we reported many kind of analyte, like for environmental application, not only environmental but also the biomedical application. So far we reported many examples. Okay, so just I'll introduce one of the recent example for the industrial application. So for industrial application, yes, so far we published many papers, but this is a scientific work. And after that, we collaborate with company to produce some actual sensor. So this is one of the example is free chlorine sensor. Free chlorine is this one, the residual chlorine for disinfection. Okay, so tap water or swimming pool or something like this. Okay, so to know the chlorine concentration in tap water or swimming pool, this is an experiment. Very long time ago, 2008, we reported this result in 2008, long time ago. As you can see, this is a result when conventional electrodes are used, plastic carbon, platinum, and gold. As you can see, the oxygen evolution start here. So on the other hand, so it means the oxidation peak of this ClO minus hypochlorite ion oxidation is overlapped here. So it is difficult to detect. On the other hand, when we use boron doped diamond electrode, this black one shows the clear peak and no oxygen evolution. This is due to the wide potential window, no oxygen evolution, and the low background current. It is a signal and the background is low. So it means the sensitivity is very high. This is the advantage of diamond. So anyway, so at this potential, we monitor this current, and when we change the concentration of chlorine, as you can see, very nice linear calibration curve, even in a low concentration. Low concentration means that it's tap water analysis is possible. So this result shows the advantage of boron doped diamond. It's a low background current and a wide potential window. So actually, we reported this one a long time ago, more than 10 years ago, 15 years ago, anyway, it's a long time ago. And then after that, this work was sleeping for a long time, more than 10 years. And then recently, the situation is changed. The importance of free chlorine sensor becoming very, very important in Japan, not only in Japan, but especially in Japan. So actually in Japan, the HACCP, this is a Japanese government fix this rule to keep international standard for food sanitation. So actually this is for Tokyo Olympic game. You know, last year in Japan, we had Tokyo Olympic game. So for the government decided to fix this rule to keep some food safety. Okay, so and then everybody must control the chlorine concentration to disinfect, for example, the washing some vegetables or something for the food. So the real-time monitoring the chlorine was very important. So then we started to collaborate with the company, and finally, very recently, this product is now commercially available. This chlorine production machine must monitor the concentration of chlorine real time online. So this is important by using our diamond electrode. Okay, so this is commercially available. Okay, so now today I want to talk about another topic of the microelectrode sensor. This is also an important direction recently. So just I'll briefly introduce some application by using microelectrode. Okay, so also we prepared this kind of micro-sized boron-doped diamond electrode. As you can see, this is a tip diameter is like 5 micrometers. This is very small. This small microelectrode can apply to the in vivo detection. Okay. So how to prepare this microelectrode? Just the same as the flat electrode by using a CVD machine, but as a substrate, we are using tungsten wire like this. Just we put this tungsten wire here, and boron-doped diamond is deposited on this tungsten wire. Okay. So just I'll introduce some example. This is one of the interesting example we reported in 2017. This is the simultaneous detection of pharmacokinetics. Pharmacokinetics means the detection of the drug, you know. So this is one of the drug. Bumetanide is a drug for loop dielectric drug. So, but it is known this drug can show the hearing loss as a side effect. This is a problem. By taking this medicine, this drug, hearing loss can be a side effect. This is a problem. So what we want to know is the relationship between the drug concentration and the hearing ability. You know, so here is in the ear. We want to know the relationship between the drug concentration and the hearing ability. So to know this relationship, we monitor. We use our diamond microelectrode here in this near pig. And also we inserted this glass electrode here. And by this, our diamond electrode, we monitor this drug concentration. And also, on the other hand, this glass electrode monitors the hearing ability. Actually, this monitors the potential. This potential reflects the hearing ability. Okay, at the same time. And then we introduce injection of this drug here. Okay. So firstly, we check the electrochemistry of bumetanide, this drug, by using boron-doped diamond electrode. As you can see, the very clear peak is observed. This background current is small. This shows a very good by using diamond electrode. Only diamond electrode can detect this one with very high sensitivity. Okay. So here is a result of the real-time measurement. As you can see, this is a before injection. The red line shows the hearing ability. As you can see, hearing ability is normal. Plus 80 millivolt is normal one. When the potential is decreasing, the hearing ability is decreasing. Okay, so it means this is healthy, normal hearing ability. On the other hand, the bumetanide concentration is 0, like this. So here, bumetanide is injected, and then, as you can see, after injection, 1 minute later, the drug, this bumetanide, comes to the ear at 1 minute later, and at the same time, the hearing ability is decreasing. So this kind of relationship between the concentration of drug and the hearing ability is monitored at the same time. This is a very interesting result. Okay. So then, 3 years later, 2020, another interesting result was shown. So time is not enough, so I must show very briefly. Anyway, when this animal take drugs, then drugs come to many organs like this. So how to come? So the timing. For example, this drug comes to here and not comes here, or so which position this drug comes. This kind of study is very difficult to detect. So to understand the medicinal effect or side effect, the in vivo real-time monitoring at multiple locations. This is an important subject for the medical doctor. So our target is a methylcobalamin. This is a drug for neuropathy, and this drug can show the effect for this neuropathy to muscle, and not only this one, but also this drug can be used to recover the deafness. This is also good. However, the medical doctor of the ear says it remains uncertain whether the action site of methylcobalamin is located inside or outside the cochlea. Cochlea is here. So inside or outside, so when the drug comes here or not comes here. So this kind of study should be known. So to understand the action site of the drug. So this is our purpose. So before applying to the in vivo detection, we studied the fundamental study of the methylcobalamin by electrochemistry. As you can see, this is the reduction peak of the methylcobalamin here. As you can see, this peak is reflects the concentration of methylcobalamin. I want to explain detail of this mechanism, but the time is not enough, so I must skip detail. But anyway, by using this current, we can monitor the concentration dependence. You know, the methylcobalamin concentration dependence can be shown by this current at this potential. So to understand this mechanism, we studied many. For example, to understand the mechanism, we use oxygen and without oxygen or something. So finally, we know the oxygen is important to show this reaction. So reduction of oxygen was accelerated with methylcobalamin reduction peak. So oxygen has a strong relation with this mechanism, we know. So finally, we concluded this is a little bit complicated mechanism like this. This is methylcobalamin, and oxygen can be important. Anyway, at this potential, the methylcobalamin concentration can be detected. So peak 1 reflects the concentration of methylcobalamin. So also, we optimize the appropriate electrochemical condition by using this experimental condition using continuous measurement study to find the optimized condition. Okay, just I must skip the detail, but anyway, finally we concluded this kind of electrochemical condition was a good one. For example, at high potential, at 1.4 volt per second, and this supply oxygen, it is important for the reaction. Then applied minus 0.7 volt, and then we monitored the current here. This is a detection potential of methylcobalamin. Then at minus 2 volt, means the reduction of the surface, means to clean the surface. So this multi-potential step can be a very good protocol. So by using this protocol, we apply to the in vivo measurement. Okay, so here the ear, here is a muscle. So we monitored at the same time. Here is a bond of diamond. Here also bond of diamond. We monitored the same time together, and we're using this optimized protocol. And this is a result of the real-time measurement of methylcobalamin. As you can see, yes, when the diamond electrode is inserted in muscle, the drug comes to the muscle. On the other hand, drug doesn't come to the cochlea, means ear. So the methylcobalamin does not reach ear. So this is interesting. This drug comes to muscle, but does not comes to ear. However, this drug can show the effect for to recover the deafness. So this is very interesting to know the mechanism of this medicine. Okay, so why this methylcobalamin does not come to the ear? So this is due to the size we guess. For example, when we use the doxorubicin, another drug, which is a smaller drug can reach to the ear on the other, in the same time. So it means the molecular size is important. Okay, I'm sorry. So time is already 25 minutes have passed. So I wanted to, okay, sorry. For the sensor application, yes, this is the Yunita-san's recent result. Also, I don't have enough time, but she will show you maybe somewhere, I guess. So anyway, this is also interesting result. So the detection of oxygen in blood, this is also good application. Very recent result. Okay, so I'm sorry, so time is not enough. So I should have talked about the CO2 reduction, but today Dr. Plastica will give a talk. So I will stop my talk, and I'm sorry. So this is also interesting topic of the CO2 reduction, but okay, so I'm sorry. Okay. So today I just introduce the application of the electrochemical sensor, but not only sensor, but also other many interesting applications, CO2 reduction also. But in the future, actually, this slide, I prepared this slide more than 10 years ago. I prepared this slide. In the near future, I thought many field our boron doped diamond can be used. I hoped at that time I showed more than 10 years ago. But actually, as I showed you, so the chlorine sensor is already commercially available now. So CO2 reduction is also very actively, and also urine analysis product is also partly commercially available now. So some of them are becoming commercially available now in these 10 years. So, but not enough now, of course, not enough now. But from now, 10 years or 20 years, maybe some of other application also can be product or commercially available. Okay, finally, thank you very much for all of our co-workers, and okay, and thank you very much for your kind attention. Okay, thank you very much.
Thank you, Professor Einaga, for the interesting presentation. Yeah, should we move on to the questions? Is there any question from the participants? Maybe you can use the raise hand feature so that we can see if you wanna. Okay, we have one, Melania Janisha Devi. Yeah, go ahead. You can ask your question. You may want to unmute, or the committee member can unmute her.
Thank you. Thank you, Prof. Einaga, for interesting presentation in electrochemistry, especially the BDD electrode. Let me ask some question. First, what is the main reason BDD has good chemical and physical stability compared to the other electrodes? And the second question, if we want to make a new electrode, is there any suggestion to get a good electrode stability? And the last question, so far, are there any weakness to using BDD electrodes? Thank you.
Okay. Okay. You gave me 3 questions. Okay. So the first one is very important. Why BDD is good? This is the first question, right? So yes, diamond is sp3 carbon, you know. So for example, the sp2 carbon electrode, of course the mechanical stability is also good because of the sp3 very strong covalent bond. And also important one, the sp3 bond of diamond surface is very inert. Inert means it is difficult to interact with other molecules. So interaction, for example, the sp2 carbon have a pi electron, so it is easy to interact with other molecule by using the interaction high. So sp3 carbon is very inert surface. So this is sometimes in this case, this is a good point to the low background current and wide potential. This is very difficult to react with some molecule. Also to water, also this is difficult. So that's why potential window is also high. So for electrochemical sensor applications, this is advantage point. But for example, for other electrocatalytic reaction, this is a very negative, very negative, worst material. Bond of diamond is worst material for the catalytic activity. Catalytic activity is less. Okay, this is the first question. Okay, and second question. What was the second question? So new electrode, you said. New
I think she said how to get the
how to get new electrode, new material, you mean?
Is that what you mean, Melania? Could you clarify a bit? Or can you restate your second question, please?
Okay.
Or maybe
maybe when she want to develop a new electrode, how to find? This is a very good question and very difficult question. Yes, I think yes, stable compound is very important. I think diamond is one of the best material for this to show the stability. Metal shows, for example, the electrocatalytic activity, and many have advantage, but for stability, I think diamond is very nice. So I also try to find another similar compound showing some stability, but yeah, this is very difficult question. I also want to find some new material. Sorry, thank you. And the third question was
the downside of carbon doping, I think, what she said. Is there any downside of carbon doping?
Downside? Sorry.
Like something negative that's
okay. Negative point of BDD. Okay.
Right.
Yes. As I told you, so there is no electrocatalytic activity. This is a negative point. So for example, when we want to detect glucose by using diamond electrode, this is difficult, impossible. So by using copper or other metal can show the oxidation peak at copper or some other metal because of the electrocatalytic reaction. On the other hand, by using boron of diamond, no peak is observed. It means no catalytic activity. This is a negative point. So long time ago, we tried to introduce some catalytic activity. One of the strategies to deposit some metal on the electrode surface, boron of diamond surface. Then this metal, we need the help of metal to introduce catalytic reaction. So this is one of the negative potential, negative point of diamond electrode. Okay.
I see. Yeah, I think that would answer the questions. Yeah, as it turns out, I think Melania posed 3 questions instead of 1. So yeah, I think
These are
we
good,
can.
good questions.
Right. Is there any other question maybe from the participants? If not, then yeah, we can conclude this session. Okay, so no further questions from everyone. Wow, that was a very interesting presentation, Professor Einaga, because before I came here, I literally have no idea about about boron doped electrodes, because my research focuses is on metals primarily. But yeah, here we have learned that highly boron doped diamond has metal-like conductivity, which can be used as electrodes, and they are physically and chemically stable compared to glassy carbon, gold, and platinum. So these electrodes can be used as biomedical sensors, wastewater treatments, for example, to detect chlorine and ozone generation. And also this technology is also being developed to prepare microelectrodes that can detect bumetanide in real time, which is very useful for our society in general. Yeah, so thank you, Professor Einaga, for the really amazing presentation. Thank you.
Thank you. Thank you very much.
Okay, so can we move on to the second speaker? Is Professor Takeshi Kondo here?
Yes.
Okay,
Can you hear me?
good. Yes, I can hear you. All right, before I give you the floor, I will introduce you first. So Professor Kondo is from Tokyo University of Science. He studied his bachelor's, master's, and doctorate degree in the Department of Applied Chemistry in the University of Tokyo, Japan. And some of his recent published work are in the Current Opinion in Electrochemistry journal, titled Recent Electroanalytical Applications of Boron-Doped Diamond Electrodes, and another one in Chemistry Letters journal, which with the title of Conductive Boron-Doped Diamond Powders or Nanoparticles for Electrochemical Applications. And today, he will share his presentation about application of screen-printed boron-doped diamond electrodes. So let me remind you again, we'll have 30 minutes for each session, including a short Q&A session at the end. So yeah, without further ado, let's welcome Professor Kondo. The time is yours. Thank you.
Okay. So can you see my slides? Okay.
Yes, we can.
Okay. So thank you very much. So first of all, I'd like to thank Yunita-san and organizers to invite me to this exciting webinar. So I enjoyed opening ceremony so much. Thank you very much. So I'm Takeshi Kondo from Tokyo University of Science. Today I'd like to talk about boron-doped diamond powder for electrochemical sensors. Okay. So as Professor Einaga lectured, so diamond itself is insulating material, but when doped with boron, this material, boron-doped diamond, can be used as an electrode material because this can exhibit metallic conductivity. So we can use this material for electrochemistry. So usually we use polycrystalline BDD thin film for diamond electrode. So this is the image of cross section of BDD thin film. So usually we use silicon wafer substrate, conductive silicon wafer substrate, and we deposit polycrystalline BDD thin film
on the surface of the substrate. So this material can show a wide potential window in aqueous and non-aqueous electrolytes like this, and this shows also low background current, low and very flat background current. So we can use this material for sensitive electroanalysis. And also, already Professor Enaga said, this has very good physical and chemical stability and good biocompatibility. And so also, Professor Enaga said the surface of diamond is very inert. So this is very anti-fouling surface. So these properties are very suitable for electroanalysis. So conventional diamond electrode is like this. This is a typical picture of our diamond electrodes. This is like 3 centimeters, this type of electrode. So this diamond electrodes requires some substrate material, conductive substrate, like silicon wafer, silicon and niobium. This is a very limited types of substrate materials. And you need high temperature for growing diamond on the surface, more than 800 degrees Celsius. And diamond and substrate materials are very hard materials, so you cannot easily get some arbitrary shape or size of the electrode. So this situation, the diamond electrode itself is very good material for electrochemistry, but due to this limitation, the size and shape of electrode is very limited, just like a small planar electrode. So we developed a BDD powder as an electrode material. So this is a conductive diamond powder with an arbitrary size from 150 nanometers to actually several tens of micrometers. So this material is a powder material, so it can be easily to be made in a composite with other materials, with some binders or other materials. So we expect this material has basic properties of BDD, like wide potential window, low background current, and physical chemical stability and biocompatibility. And plus, this is a powdered electrode material. So this material has large specific surface area, and this can be applied to printed electrodes or painted electrodes by preparing ink containing BDD powder and other binder materials. So in this lecture, at first, I'd like to introduce this material, BDD powder, at first, and I will talk about some application on BDD powder printed electrodes. So for preparation of BDD powder, this is basically the same as when we prepare BDD film. So we used diamond powder as a substrate. This is a commercially available insulating diamond powder. This can be get as our this powder is commercially available as an abrasive, abrasive. So different sizes of powder can be obtained. Then we put insulating diamond powder on some holder, then deposited BDD layer on the surface of diamond powder. then we can obtain conductive powder, BDD powder, BDDP. So these are typical SEM images of diamond powder before CVD and after CVD. So we can use, we can choose different sizes of diamond powder as substrate, and we can obtain, we can get different sizes of BDD powder, conductive diamond powder. So basically the size and the shape are the same even after CVD. So this means by choosing a corresponding size of substrate, you can obtain desired size of BDD powder, conductive diamond powder, from like 100 nanometers to several micrometer sized diamond powder. So, but basically the size and the shape are almost same before and after CVD, but morphology of the surface was little bit slightly different. So before CVD, this is a substrate material. This has smooth surface, but after CVD, so you can see some rough surface. So we think nanocrystalline BDD was deposited on the surface of a substrate. So this powder was covered by nanocrystalline BDD. Then this powder can exhibit good electrical conductivity. Okay, then this is size distribution of diamond powder before CVD and after CVD, BBD powder. So you can see that the peak size was slightly increased after the CVD, but basically, as I said, basically the size is almost same before and after CVD. So you can obtain monomodal size distribution of BDDP. Then, so next I will talk about BDD printed electrode for electrochemical sensors. So BDD electrodes is, so as I told, a very good electrochemical electrode material for sensitive electroanalysis based on a wide potential window and low background current. And on the other hand, screen printed electrode is also good for electroanalysis because this can be produced at low cost, and this is basically lightweight and disposable, a very cheap electrode. So you can prepare 3 electrodes on one chip. Then you can use this as an electrochemical cell. So when we can obtain, when we can create screen printed BDD electrode, it should be low cost, lightweight, disposable, and sensitive electrode for electroanalysis. Very sensitive and very cheap electrode can be obtained by printing BDD on a cheap substrate. So we prepared BDDP ink for printed electrodes. This contains BDDP and some, this is the insulating binder, polyester resin, and these are solvent. This is to dissolve polyester resin, and this is used for also solvent. Then we fabricated screen printed electrode by screen printing. We used polyimide film as a substrate or PET film as a substrate. Then we this is a current collector carbon, and silver paste for lead and resist. We printed BDD powder ink, and we can obtain this type of the single electrode printed electrode. So this is a typical photograph of BDDP printed electrodes. So these are SEM images of this area, electrode area. You can see densely packed BDD powder on the surface. So this can be function as a electrode. So this figure shows cyclic bottom grams of so ferrocyanide at BDD printed electrodes and carbon printed electrodes. You can see that the current response is almost same at carbon printed electrodes and BDDP printed electrodes, but the background current is much smaller at BDDP printed electrodes. So low background current was observed at the BDD printed electrodes. So this should be effective for sensitive electrochemical detection with a large signal to background ratio. So this is one application of one demonstration of BDDP printed electrode for electroanalysis. So we detected ciprofloxacin, which is an antibacterial drug. So this can be this is desired to be detected at low concentration from human urine or some environmental waters. So we compared LSB, linear sweep bottom gram of ciprofloxacin, CIP at BDD conventional BDD thin film electrodes and BDDP printed electrodes. So as you can see, the current response is very similar, and background current level is almost same. So this can be used for this can exhibit sensitive electrochemical detection of CIP as this conventional BDD thin film can exhibit. So also we check the detection of CIP from artificial urine. So we found that CIP can be detected even from artificial urine solution. So we diluted 100 times by phosphate buffer solution. Then very clear anodic peak was observed for this concentration range. So this showed very good calibration curve, and the limit of detection was almost 0.9 micromolar. Then the concentration of CIP from actual urine of patient taking CIP is reported to be this concentration range. So we can detect this concentration by using 100 whole diluted solution by using BDDP printed electrode. Then the BDDP printed electrode can be also applied to other sensors like glucose sensor. So we fabricated glucose sensor by using this. So in this case, we use cobalt ferrocyanine as an catalyst for hydrogen peroxide oxidation. So we prepared ink containing BDDP and cobalt ferrocyanine. At first, we printed this ink on the surface. Then after that, we deposited glucose oxidase layer by electropolymerization of PPD, polyphenol. Then this is a enzyme immobilized layer. So this can work as a glucose sensor. Diamond BDD itself cannot detect glucose directly, so we need some catalyst or enzyme for glucose sensing. This is a amperometric detection of glucose. So when we added glucose to the solution, the current response increased linearly. So we can get very good calibration curve for glucose detection. And so the current response is basically same as when we used carbon electrode for this structure, but the baseline was very stable for diamond electrode. So this should be a very good sensor platform for this type of enzyme based biosensors. And we also investigate the effect of binder to BDDP ratio in the ink. So when the binder to BDDP ratio is small, so I mean when you use much BDDP, so this should be our planar type electrode, conventional usual planar type electrode with linear diffusion of analyte. But in the case of large binder to BDDP ratio, so much binder and with little BDDP, this should be like a microelectrode type behavior should be observed with hemispherical diffusion layer. So this situation is also suitable for sensitive analysis. So small current, but the signal to background ratio is very large. So this is also one of sensitive electrochemical sensors. Then these are second bottom grams of peripheral cyanide, and we prepared screen printed electrode with different binder to BDDP ratio. When the ratio is small, so I mean much BDDP, the behavior is very normal for planar type electrode. But when the binder ratio increased, the CV behavior gradually changed, and at last, this showed a sigmoidal shape, which is typical for microelectrode. So this means type of diffusion on the surface was changed by binder to BDDP ratio. So we check the conductive domain on the surface of printed electrode. When the binder to BDDP ratio is small, so whole surface is conductive. So this is elemental mapping of kappa after kappa electrode deposition. So bright area, there are kappa. So this is conductive domain. But in the case of large binder to BDDP ratio, so micrometer sized conductive domain was isolated each other with some distance. So this situation is should be effective for microelectrode effect. So also we also check this behavior by impedance spectroscopy. These are Nike spots for peripheral cyanide at different binder to BDD ratio. So the behavior gradually changed, and for this electrode, charge transfer resistance is very large, and diffusion behavior was very different from the planar type electrode. So we confirmed the transition of diffusion type from planar linear diffusion to hemispherical diffusion. Then we demonstrate the electrochemical detection of 8-OHDG, which is a oxidative marker, biomarker. So this can be this concentration increased in biological fluid when the body was stressed by oxidation. So this should be very important, one of important biomarkers. Then these are differential pulse grams of 8-OHDG at conventional polycrystalline BDD and BDDP printed electrode with small binder to BDDP ratio and large binder to BDDP ratio. When the binder to BDDP ratio is large, the current itself is very small, but the background current is very, very small. So signal to background ratio is the largest for this electrode, much larger than conventional polycrystalline BDD thin film. So this should be, in some case, this should be very effective, very sensitive to some electrochemical analysis. Okay, so I will conclude this my talk. So at first I introduced new material, BDD powder, as a conductive diamond powder material, and I introduced some application to screen print diamond electrodes. So basically, the screen printed diamond electrode is very can offer sensitive electrochemical detection as basically same as a conventional BDD thin film electrode. But in some case, this can be much large signal to background ratio so this can be useful for electrochemical detection. Okay. So in this talk, I talked about application to some sensing application for using screen printed electrodes. But this is a very basic material. So this can be used for other types of applications like energy devices. So we also try to use this material for cathode catalyst support for fuel cell. And also we use this type of material for supercapacitors electrodes because this has very large specific surface area and wide potential window. So you can apply large cell voltage to the device. Then also we try to apply this for water treatment. So recently we have published some paper for BDDP packed flow cell. The packed bed can function as an anode for water treatment. You can decompose some organic compounds to CO2. Okay, so and many collaborators used this material, and there are many published papers in worldwide. So if you if you are interested in this material, so you can use this material, and so I'm very welcome to new collaboration by using this material. Okay, thank you very much. So my talk is finished. Thank you very much.
Thank you. Thank you for very much, Professor Kondo. So is there any question from the participants? If so, you can use the raise hand feature or type your question in the chat box. That's also work. Okay, there are 3. Let's see who raised their hand first. Yogi Mirza, are you there? Yeah, you can go ahead, Yogi. Is Yogi still here? Hello? Okay. So can the
He's chatting.
somebody sorry, I think this is like a technical issue. Can the committee please oh, his mic cannot work. Okay, yeah, can the committee member help with this? Yogi Mirza wants to pose his question.
My voice.
Oh, yes. Yeah, we can hear you now. Yeah, go ahead, Yogi.
Okay, thank you for the time, and maybe I introduce myself. My name is Yogi Mirza from Mathematical Engineering, Institute Teknologi of Kalimantan. Thank you for the opportunity. Maybe my question to you, sir, maybe the first, why we need the BDD in the form of powder, and what trying to achieve with this form, and what is different with the normal BDD except for the size. And the second question, does the binder did use is affect the sensitivity of the sensor, and what type the binder is good for the sensors? Maybe that's my question.
Okay. Okay. So you have 2 questions, but okay. So first one more please. First question.
The first question is why we need the BDD in powder form, what trying to achieve with this form, and is that different with the normal BDD except for the size?
The size, so you so you're talk about the size.
So he asked why would we want this BDD in powder form? Besides the difference in particle size, is there any other difference between the conventional BDD and the powder BDD?
Thank you. So okay. So yeah, so I didn't talk about the effect of size. So so basically a basic property is same to conventional film and powder, but this has some so okay, so this has very large specific surface area. So when you apply some this type of electrode, so you need large specific surface area. And for printed electrodes, so you can create this type of electrode with So this can be applied to mass production. So very cheap. So you need very small amount of diamond for one electrode. So in this case, so for one batch of CVD process, so you can obtain several tens of printed electrodes by one batch of BDDP. So this should be suitable for mass production. But the basic properties are almost same. So you can create very cheap and light or flexible electrodes by using this type of powder electrode. Okay. Then, so okay, for the first question.
Yeah. So
okay.
yeah.
Okay. For second.
Sorry. I think that Yogi Mirza has the second question, which is how sensitive is the higher binder ratio of BDD, and what is the binder material that you usually use?
So binder is basically just an insulator, because we want to so compounds should be reacted at this local area. So the binder should be insulating. So we use some resin, insulating resin for the binder. So we have not changed the binder material.
Oh, I see. Yeah. So the binder is insulating, so that's why you would get different kind of what is it, microelectrode array effect? Yes.
Insulating area. Exposed binder. Only this area is exposed. Has exposed BDDP. So the reactive area is very limited to this area. These are insulating. Okay.
All right. That's why they have different kind of response. Yeah. Right. So to summarize, what's the difference between the BDD in powder form and the conventional form is basically their properties are the same, but you would have more flexibility in how you would fabricate your electrodes. And with a higher surface area with the powder, you would have higher properties of the properties that we want to use with this electrode. And the sensitivity of the higher binder ratio is basically a different thing. You would get different kind of properties with different binder ratio to BDD. So yeah. Thank you, Professor Kondo, for your answers. Yeah. This has been welcome. So this has been really interesting. Really, yeah. This is also my first time learning about this material. So yeah, initially when we have the conventional diamond electrodes, it would require substrates such as silicon, niobium, which are very hard and they're difficult to be processed for specific geometric applications, and it would require higher temperature. So Professor Kondo here developed a new kind of BDD powder, which then would make it easier for us to further make them into different shapes or different applications. And yeah, as he also explained before, that when we use different binder ratio, we would get a different microelectrodes. Sorry. There are background noise. Okay, maybe it's just me. Yeah, so I think that's really interesting to learn. Yeah. Maybe before we move on, to the next speaker, is there any other question? One more question, maybe from the audience. We have Hiskia Alpha. Do you still want to ask your question?
Thank you, moderator, and good morning, Professor Kondo. I am Hiskia Alpha from Materials and Metallurgical Engineering ITK. Do you hear my voice?
Yes.
Thank you very much. I want to ask you just one question. Why do you use molybdenum powder as the substrate for this BDD? Because in my opinion, why don't use like cheaper alternatives like silicon or other powder materials? Is it because special properties of molybdenum? Thank you.
Okay, thank you. Yes, this is a standard device for plasma CVD. So this is molybdenum. This is so in this figure. This is a very flat type, but this has some structure for plasma to get good plasma formation. So, and molybdenum is very stable for high temperature material. So this is the standard material for this device. Yes. So this is just for the container for this powder. So this is very stable under high temperature. Okay.
Also, it's not actually used in the electrode. That's just the holder when during the deposition.
So this is just a holder. So this is electrodes does not contain any molybdenum from this holder. Yes.
I see. Yeah, and also silicon is also mentioned that it's also being used before, right?
Oh, okay.
Yeah. Okay.
So,
thank you.
Yeah. So thank you very much, Professor Kondo, for the explanation.
Thank you for questioning.
Okay, so I think we can limit the question to two question askers. So thank you, Professor Kondo, for your kind presentation and answering the questions. We learned a lot from you. Yeah.
Thank you very much, Leo.
Thank you. Okay. Right, that was a really interesting subject still. Yeah, we learned that we can get different properties with different binder ratio, and also by changing the size of the particles into powder particles, we can make them into different geometry or shapes that you would wish for. And with that, let's give a round of applause to Professor Kondo once again. Thank you, Professor. And let's move on to the third speaker. Is Professor Ivandini here already?
Yes, I'm here.
Okay. Thank you. Okay, so before I give you the time to present, let me introduce you first. Professor Ivandini Tribidasari Anggradingrum is from University of Indonesia. She obtained her bachelor's and master's degree from the Department of Chemistry, Universitas Indonesia. And then she went to get her doctorate degree in electrochemistry at the University of Tokyo, Japan. One of her many accomplishments are becoming the chief editor of Makara Journal of Science and awarded with Habibi Awards in 2018. So today, she will share her insight on the modification of polycrystalline boron-doped diamond films for sensors and biosensors. So let me remind you again that we will have 30 minutes for each session that would include the short Q&A sessions at the end. So without any further ado, let's welcome Professor Ivandini to the floor. It is yours.
Thank you, Leah. I want to share my my PowerPoint. So, okay. Okay, my title is about modification of polycrystalline boron doped diamond electrodes for sensors and biosensors. And next, you have seen this figure in our previous presentation with Prof. Enaga and Prof. Kondo. Actually, this is very legend in our group, boron doped diamond group. We have always this figure. Okay, so we know from our previous speaker that boron doped diamond is superior because of its low background current, wide potential windows, and also high stability and good biocompatibility. Accordingly, many reports about its application for sensors and biosensors. And also some application regarding electrochemistry or electrochemical technique are also reported. But in fact, boron doped diamond is not electroactive to some chemicals. For example, glucose, arsenic, oxygen, also peroxide. In this case, we have to modify its surface, then we can get a good result for this. So before we modify the surface, we have to study about how to make how to synthesize the boron doped diamond films. I think Professor Enaga already showed this, maybe Professor Kondo also. And actually, the reaction is very simple. Hydrogen plus hydrocarbon. We can use methanol, we can use methane, and actually should be very, very small molecule of hydrocarbon, because we want to cut and then reform again to be a diamond. And after that, we can produce again the hydrogen. But why we need hydrogen for this process? So actually here, roughly, hydrogen will be introduced into this machine, chemical vapor deposition machine. Yeah. So hydrogen will be introduced here, and then with high temperature and high pressure, the hydrogen will form hydrogen radicals, and then form plasma. You know, plasma is like ionic phase of atom. And then we introduce the carbon inside here, and the hydrogen radicals will attack the hydrocarbon. We can get like this. We can get carbon-carbon atom, and then if we use seeding here, seeds, we can make it as a template to the crystal formation. Then the carbon will rearrange to form a diamond structure here. So because we use hydrogen, then we have some hydrogen on the surface. So if we measure with XPS, we will have some hydrogen on the surface, which is actually in the atmosphere gradually oxidized to be oxidized surface. But sometimes it is very long time, and then generally we just oxidize with electrochemistry, and we get some oxygen surface on the surface. But then after we synthesize the diamond films, how to characterize? The easier is using SEM. We can get some crystal already grown on the surface, and after 8 hours we can get around 5 micrometer particles, and with the around that thickness also. But in this case we cannot confirm this is diamond or not. So diamond is characterized with its sp3 sp3 coordination. So all should be sp3, and if we want to characterize this, we have to use Raman spectroscopy. Then if we have this peak at 1333 per centimeters, so this is sp3. But if we have this in 1500 something, should be sp2. And good diamond, good quality of diamond should be only this, without this. But sometimes if we put boron, why we need boron inside? Because we want, because diamond film, diamond actually doesn't have conductivity, as there is no electron on the surface, because you know, diamond carbon has four electron, which then occupied within sp3 coordination. Then there is no electron, there no conductivity. So we put boron to improve its conductivity. Then it will have some defect, then some electrons to transfer the electrical. But it should be no sp2 form, because if sp2, then not diamond anymore. Yeah, if we form this, then maybe, but maybe we can get this and small amount of this to have good conductivity. And why sp2 can form? Yeah, actually, diamond is metastable of carbon allotrope version. Then we need high temperature and high pressure to form diamond. But it's very easy to form sp2. Or if we have in this reaction oxygen, the carbon will combine with oxygen to form carbon monoxide or carbon dioxide, or then sp2. Yeah, to form sp2 is actually very difficult. Then we have to put more hydrogen to confirm the reaction will form diamond. Okay, next. Yeah, so the surface should be like this. Yeah, but don't worry, we can oxidize to be like this. And if we want again hydrogen surface, we can reduce in very, very high negative potential. Then actually they can go back to hydrogen termination. Next, but our topic is about how to modify the surface of boron dot diamond. Actually, there are 5 methods are reported. We will discuss one by one. First, the most easily is by absorption technique. So we paint or drop the surface with ion solution. For example, we want to modify diamond with gold, so we drop some volume, very small volume actually of gold ion solution. Or we can also immerse. We put diamond inside in the solution, yeah, and then we dry it. We can get their attached on the surface of diamond. And then if we measure by AFM, it should be like this. We can also use solidal reaction. So we put the solution of diamond and then make some heating and then become gel and dry and then little bit like this. So this is reported for ruthenium, lead, and iridium, and from this side maybe this is the diamond films and the particle of metals on the surface. However, as diamond is sp3 coordination, sp3 structure, so it's very difficult to form chemical bond on the surface. Then this is become very weak. This interaction become very weak. Yeah, like you just put some solution on the table, for example, and then if you want to clean, it's easy to clean. This is also occur with diamond film. So next, the other method is using electrochemical deposition method. How to perform that? If adsorption methods only drop or paint, in this we put negative potential or other potential. For example, negative potential here in the electrode, and because the metal ions is generally positive charge, they will attract to the surface of the diamond, and if the energy enough from diamond will pass the energy to the particles, and there will be reduced to be metal particles. So this is the most easier because we can get quite uniform result. Yeah, and if we already oxidize the surface, become oxygen termination, it will be more easier because hydrogen with metals is not so familiar, so interaction is very less, but with oxygen the interaction will be better. Then you can do this method with much better result than using the adsorption technique. Okay, so but we will have like this also. So diamond and some particle on the surface. Then stability is very less for this kind of modification. But this is the most simple modification. So there are so many reports about using electrochemical technique for to modify boron doped diamond for sensors. We can this is only some, but maybe more of the report about this. And they are using many kinds of metals like iridium, platinum, gold, yeah, anything. And the other method is using okay. So we can see this is quite uniform, but actually if we zoom this picture, we can find that some small, some big particles. Then my student try to anneal this. Yeah, after modification, she annealing this. Annealing means heating in very high temperatures. I think he used around 600 Celsius degree. Then he can get very nice distribution of the particles. Yeah. So, but after that annealing, some passivation occurs. So she just again doing electrochemical deposition, and then she can get fresh, but the deposited material will be on the surface of the previous one, so it becomes a very good uniform of the modification. And if we check the stability with ultrasonication, so we use ultrasonication to clean boron doped diamond actually, and using ultrasonication we can get very stable result then compared to not annealing technique. So then the other method is metal modification at boron doped diamond surface using ion implantation. So what is doing with what we are doing with this? We implant, yeah. So we are doing accelerator to shot the particle on the surface of diamond. So like this, using acceleration, the particle will half buried on the surface of diamond. Then actually for doing this, some calculation should be performed, yeah, because we want modification but still SP3 surface. If it changes to be SP2, then it's not BDD film again. So we need to have good calculation. Then it's still SP3 because this acceleration maybe will will destroy the SP3 surface. So using this method, actually we can get very good stability also, but yeah, it's difficult to find this method again. Previously, I worked this in Professor Enaga laboratory using accelerator in Tokyo University, but then after the professor retired, I mean professor in Tokyo University, then it's difficult to find to make this material again. So this is good but difficult. Then we stop this experiment. And other thing is we try to modify the diamond first. Yeah. Okay. Oxygen surface may be good to attach the metal, but still there are no binding, no chemical binding. So we try to have modification with aniline. Sorry, allylamine. Sorry, allylamine. So the structure is this: the allylamine, and then if we drop some solution, some volume of solution on the surface of diamond, and then irradiation with UV lamp, and this structure will be formed. So this double bond will destroy, and then the allylamine will make bonding with diamond, and on the surface we will have amine surface, and everybody know that good interaction between nitrogen and gold nanoparticles. So we prepare gold nanoparticles outside, and then try to attach in this surface. So nitrogen still have a pair of electron, free electron, and they can do chemical bonds. So here is the conformation with XPS. We can see that some nitrogen on the surface, and then nitrogen on the surface, and then gold on the surface, and okay. And okay, we try also with this is gold nanoparticle. Then we try also with gold palladium nanoparticle. So we have gold nanoparticles, and then we put in the palladium solution, palladium ion solution, and using sodium borohydrate to reduce palladium, and palladium will attach to the surface of gold, and then we try to attach this. So to attach in this surface, and okay, actually the interaction is between gold and amine also, because palladium and amine functional group may be not suitable. So but we can attach this if we don't use many palladium. So this flower structure still expose some gold, and then we can attach this particle here. And okay, so this is the gold to carbon ratio. Using the previous method, we can attach with gold here, but using palladium, we have both gold and palladium atom particles on the surface of boron doped diamond. So we try to use that both modification for oxygen sensors. Then we can see we have a little bit better sensitivity, but very high sensitivity when we have palladium, and it's also decrease the limit of detection. We try also with copper gold nanoparticles. Why copper? Because copper is very good catalytic, has good catalytic performance. So we synthesize copper nanoparticles and then cover with gold, and we can get like this, and we attach to the surface of diamond, and we use again for oxygen sensor. Then we can see that better result with better coverage when we are using copper, and also better results for oxygen sensors. The last part is about electrochemiluminescence at metal modified boron doped diamond. I think Dr. Irham graduate from KU University also, and previously he was my student in UI. He will discuss this a little more detail, but here just to introduce. So electrochemiluminescence means luminescence or light produced because of electrochemistry process. So like this, if we have luminophore, which is oxidized on the surface of boron doped on electrode, for example, we can use boron doped diamond, of course. And then after oxidation, it will give light as luminescence, and then because initially from oxidation from electrochemistry process, and the result is luminescence, so become electrochemiluminescence. We are using luminol as the luminophore to produce the luminescence, and we try to use measure hydrogen peroxide by using the electrochemiluminescence. So if we have only luminol will be oxide, and then the oxidation form change the structure, and then and then they will give luminescence as the result. But if we are using if we are if we put hydrogen peroxide inside the system, this is change. I think in this step, in this step change, the radical oxygen from hydrogen peroxide will change the structure, and then we can get a higher intensity if we have hydrogen peroxide here. And with the concentration of hydrogen peroxide, it can we can get a calibration curve, because the intensity also increase. And this is the comparison for H2O2 sensors. From literature, we have this is by using enzyme, by modifying diamond with platinum, but this is colorimetry, this is cyclic voltammetry using amperometry, and etc. We can get a little bit better result with using this. Okay, next. But since our title is modification of boron doped diamond, so I try to modify boron doped diamond with gold here. So we have this here. Actually, my student put pani here. Pani is polymer, polyaniline, polymer of polyaniline, and then attach the gold here. So as we can see here, if the boron doped diamond is the black one, the electrochemiluminescence result, the black one with gold, higher intensity can be achieved. And we also try with Prussian blue attached on the surface. This is maybe not very uniform, but we just want to try, we want to check the electrochemiluminescence. So this is with the gold, and this is with the Prussian blue. And we try to use this to measure H2O2, hydrogen peroxide. We can get linear result at gold boron doped diamond, and also at Prussian blue boron doped diamond. Here is measured by electrochemiluminescence, not electrochemistry. And comparison between the unmodified boron doped diamond with the modified boron doped diamond, we can get actually better result. Better result with the modification. A little bit with Prussian blue, I think, because here the Prussian blue only have iron around 11%, while in gold, the gold particle is around 45%. As the conclusion, to increase the stability of the modifying metal particles at boron doped diamond, maybe ion implantation and photochemical is suitable. However, ion implantation method is impractical due to the instrumentation. Well, both methods have disadvantage due to the limitation of the deposit particle at the surface of diamond. Actually, by using electrochemical methods or physical absorption, we can get more particles on the surface. And then development of the method to increase the deposited particle on the BDD surface is still necessary. Then modification of boron doped diamond films with metal not only increase its electrochemical properties, but also its electrochemiluminescence. So I cannot do this work without my PhD, actually, from Ombusho scholarship, and also more than the Monbusho and Naga Sensei take care of me for very long time until now to do research in our university. And I got also some funding from GSPS, from UI, from my department, from Osaka Gas Foundation, and Ristek Dikti, and yeah, from some also helping. And thank you for your kind attention.
Thank you very much, Professor Ifandini. So that was a really interesting presentation. Is there any question from the audience? If so, you can either type your question in the chat box or use the raise hand feature so that I can see. Any question? Okay, we have one from Casey Defiant. Yeah. Can the committee member please help so that Casey can ask her question? Allow her to open her mic. Yeah, go ahead, Casey.
I cannot hear your voice. Maybe you are still mute.
Yeah, me neither.
That's it. Can you hear my voice?
Yes. Yes. Very
Okay.
clear.
Okay. Let me start the question. It mentioned before there is a deposit process on the modification of BDD, and my question is how to determine the deposit time of the metal particles to reach the surface of BDD.
Okay. Okay. So for example, for this method, yeah, we modify with electrochemical techniques. Then we want to measure glucose, for example. Then what we will do is we using amperometry, for example, then try for 5 minutes and check for glucose oxidation. Try again maybe 10 minutes and check for glucose oxidation. The best ratio between the signal and the background is selected as the optimum condition to deposit boron, to deposit the metal on boron doped diamond. I think that's the technique. Is it help? Did it answer your question?
Okay, so we just check the time gradually to make sure that the particles is already.
Yeah. I think no other way. First, we try with 1 minute check, and then we put more metals, 2 minutes check, and then yeah, something like that. Don't worry to don't forget to measure also the background, so you can get because with the metal deposition, the background will increase also, and we want the best ratio between signal and background to make the optimum condition.
Maybe I want to add more questions. So is it possible that we're gonna reach hours to make sure the deposit in BDD in hours?
Excuse me, sorry, I'm not clear.
The time. Is
The
it
time?
possible that we reach hours?
Oh, no. I think because the disadvantage of modify boron doped diamond is decrease the quality of diamond. For example, first we sorry. So Okay, so first we mentioned the advantage of diamond is we have low background current, yeah, wide potential window, high stability. If we modify the boron doped diamond with metals, we will increase this. Why? Because metals actually attract the solution, water especially, and then will increase the background current. And if we have high background current, then what the limit of detection will decrease. We cannot measure until very low concentration. That's the first. The second one is a wide potential window. If we modify the boron doped diamond, we will have the window like the metals. So decrease the window, the whiteness is decreased. Then so actually, which is the higher so the particle with higher conductivity will be limiting the potential window. So what we can do is we optimize between advantage and the disadvantage. Then it means we have to put as small as possible metals on the surface. Then we have to use very low concentration of the metal solution. Also, we have to put very small amount of iron. So generally 5-10 minutes is enough. Yeah, we try 1, 2, 3, yeah, or 2, 4, 6. Yeah, not more than that. For hours, maybe become all covered with metals, and then we lose the good property of boron doped diamond. So
for the answers.
Okay, thank you for the question.
Right. So yeah, if we modify too much, then
Yeah,
it's
yeah,
not gonna be, it's not so
like,
gonna be no
we
diamond.
put makeup too much, then
Right.
yeah,
It's the
we
skin.
lose our identity.
True. Okay. Is there any other question from the audience? Maybe one more? No? Okay. Yeah, it's been an interesting discussion. So thank you, Professor Ivandini. Let me summarize a little bit. So Professor Ivandini showed us how to prepare the BDD films, and then we can characterize the synthesized BDD using SEM and Raman spectrum to confirm the sp3 electron configuration. And then why would we need boron in the diamond is because diamond is not really conductive, so boron is to improve the conductivity. And there are 5 different methods to modify the surface, which is to utilize adsorption technique, and then electrochemical deposition, ion implantation, photochemical modification, and then electrochemiluminescence. So it's mouthful. To increase the stability of the BDD. Yeah, so yeah, that was a very interesting presentation. So thank you, Professor Ivandini. Thank you.
And thank you also for inviting me.
Yeah, it's our pleasure, definitely. Right. Before we move on to the 4th speaker, maybe I would like to remind everyone to fill in the G form so that you can claim your certificate. Yeah, maybe the committee member can share the G form in the chat box for everyone. Okay, so with that aside, let's welcome our 4th speaker, Dr. Prastika Krisma Jiwanti from Erlangga University. Is Dr. Prastika here?
Yes, good morning.
Okay, good morning. So yeah, let me introduce her first. She got her bachelor degree from the Department of Chemistry in Universitas Indonesia, and her master's and doctorate degree are from Department of Chemistry in Keio University, Japan. She has many published papers related to her expertise, such as a review on carbon-based electrodes for electrochemical sensors of quinolone antibiotics in Chemistry Select, which was published this year, 2022. And another example is her scientific article titled Electrochemical Study of Carbon Dioxide Reduction on Ti3C2TX Modified Boron Doped Diamond Electrode, which was published in Inorganic Chemistry Communications this year too, 2022. And yeah, so today she will present to us about modified BDD electrodes for carbon dioxide reduction. So we will also have 30 minutes for this session, including the short Q&A session at the end. So yeah, without any further ado, let's welcome Dr. Prastika to the floor.
Okay, thank you, Ms. Leah. Let me share my screen. Okay, is it clear enough to see?
Yes, we can see it.
Oh, sorry. Okay. Okay, so let me start my presentations. Good morning, everyone. So actually, I'm very nervous this morning because this is, I think, the first time I need to talk about my works. Yeah, like my own works after graduations in 2019. So I'm the student from Professor Evandini. So she's my supervisor in bachelor degree, as well as Professor Einaga. So he is my supervisor in master and PhD degree when I study in Keio University. So that's why I'm very nervous now. Okay, so now I will talk about my works around 3 years after my graduations and after I joined Universitas Airlangga. So the title is Diamond Material for Electrochemical Conversions, and also a bit about sensor application as well. Okay, so now I live in Surabaya. So before also in Jakarta and also in Japan, and maybe the map will be like this. So if you already visit Surabaya, you will know this icon. So this is the iconic of Surabaya city. And I live with my husband and my little baby boy. And I belong to Department of Nanotechnology Engineering, Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga. So I joined this university from 2019, just after my graduations, my PhD graduations. So this faculty actually still new, established in 2019 also. So we just still not have so many students and not doing a dissertation yet. So this is actually quite difficult to build the research group here, but I'm trying to work. So that's why now I can present some our new works, and also I will also introduce about CO2 reductions in when I'm doing in PhD study and also my current works. So I think Professor Evandini and Professor Einaga and Professor Kondo as well already talked about this BDD electrode. I think this BDD electrode is not as famous as other materials, especially in Indonesia. So Professor Evandini, I think the first professor working this in Indonesia, and now we'll continue to study this and develop the BDD application in Indonesia. So the BDD electrode synthesized in MPA-CVD machines using 3-methoxyboron and acetone, and this, you can see this a polycrystalline BDD. You can see this is the real BDD, and also this is the SEM image of the surface of BDD electrodes. There are many applications, especially we can't do electrochemical applications with boron doped diamond electrode. It has a superior behavior actually. It has a wide potential window compared to another electrode. It has a low background current, which is very good for sensor applications, and it has a high stability of physical and chemical stability. Other than a polycrystalline BDD electrode, we also have a boron diamond nanoparticles, we can use this. I think Professor Kondo already an expert in it. So we can use this for sensor application by screen print and making a screen printed electrode and become cheaper, and we can use this for sensor applications. Okay, so this is some work. So there are many works other than this actually already published, like this CO2 reduction on board the diamond electrodes and the production of C2C3 species. So I work with this under Professor Ainaga supervisions, and then also some publications with Professor Ivandini, together also with Professor Ainaga. Okay, so now in Universitas Airlangga, I'm working with this for electrochemistry applications using carbon-based material. So basically I'm working with diamond material as well as other carbon-based material, for example, glassy carbon, graphene, and other materials. So we use so my current work's working with the biosensor and medical sensor because our university mostly focusing on health science. So that's why I'm working with the biosensor and or medical sensor. So we have working with antibiotic sensor, artificial sweetener sensor, and also other pharmaceutical sensor. And another one also we're working with heavy metal sensor. And also I continue CO2 reductions. So I finished PhD degree by working with CO2 reduction. So that's why I still want to continue to study about CO2 reduction, especially using boron diamond as well. Okay, so firstly, we start with antibiotic sensor. So some antibiotic already used, for example, levofloxacin, ofloxacin, ciprofloxacin, and azithromycin is a type of fluoroquinolone antibiotics, and it's usually used by humans when we have a COVID-19 2 or 3 years before. Some researcher or some doctors in the world use azithromycin as an antibiotic treatment for COVID-19. So that's why actually the use of antibiotics for humans is allowed. And other than that, the antibiotics also used in animals, yeah, to support their growth. So that's why some of this usually directly goes into the food from animals, and if we consume this a lot, then it may produce heart problem, abdominal discomfort, tendon rupture, and also bacterial resistance. So that's why we need a sensor. Like, for example, if we make a sensor like this, then we can just directly detect if we have antibiotics in the foods from animals that we consume every day, or it can also sense in the human body as well. So by this project, we also we have already produced an article review and some works in article based of experiment as well. So this just published this year actually. Okay, so the first topic, so we make a sensor of levofloxacin antibiotics on the surface of boron diamond electrode decorated by nickel nanoparticles. So we modified nickel nanoparticles by electrochemical depositions, as maybe Professor Ivandini already talked a lot about this. So we modified nickel nanoparticles on the surface of boron diamond electrode. As you can see here, the SEM image like this, and we have very small nanoparticle as well, around 1% nickel nanoparticles on the surface of PDD. And we have allowed, well, as Professor Ivandini, it's like using a makeup, and then the PDD will lose this identity. So that's why we just modify a small amount of nickel to improve the catalytic activity. And we have like this SEM image. So we still have the property of BDD, and also we have the property of nickel nanoparticles as well. So we get the signal of antibiotics, the oxidations of levofloxacin at the potential around 1 volt, like this. So that's why after this, we can detect the levofloxacin and optimize the condition of the sensor. Okay, so we try to measure the scan rate, and we get the irreversible process of antibiotic sensing or the oxidations of levofloxacin, and it also conclude that this process is diffusion control. And we have the LOD, small LOD, 11.13 micromolar limit of detections by using like a linear calibrations with different concentration of levofloxacin. And the second works, so we tried also the levofloxacin interference. For example, we use a square wave voltammetry method, and we put the interference such as urea, glucose, ascorbic acid, and also in a real sample, which is the urine sample, and we still get good stability, good selectivity, and also we can still detect the levofloxacin in the urine sample as well. And this is the second works about ciprofloxacin or antibiotic sensor, which is a ciprofloxacin antibiotic. We make a different, or we use the different boron concentration in diamond electrode because, for example, the behavior of boron diamond electrode will be different if we use a boron doping level, a different boron doping level, and also if we make the surface terminations different, then the behavior will be different. And also sp2 carbon impurities also make a different behavior in BDD electrode. So we tried to make a sensor with a different concentration of boron doping. We got the Raman spectra like this, and also the CV. Can see here that the potential window when we use 1%, 0.5%, and 0.1%, then the potential window will be different. We got the longest potential window with the BDD 1%. And we studied the signal per background ratio in 0.1%, 0.5%, and 1% as well. And we got the highest signal per background ratio in 1% BDD. And we tried here for ciprofloxacin electrochemical sensor, and we got the lowest limit of detections on the surface of 0.1%. In 1% boron diamond electrode. So BDD 1% shows an optimum condition for a ciprofloxacin sensor with the lowest limit of detections. And we also tried in pharmaceutical tablet and also milk sample, and we got the good recovery for this. And another works also, we tried the levofloxacin electrochemical sensor on boron doped nanopowder based screen printed electrode. So the works will be like this. We tried the SEM image. We have the nanoparticle size around 220 nanometers. And by this one also, we get the signal of levofloxacin at raw potential 0.84. And we tried to measure the sensitivity and limit of detections using screen printed electrode. So usually the working electrode in this screen printed electrode, in commercial screen printed electrode, will be carbon. And we modified with the boron doped diamond nano powder. We get the higher sensitivity as well as the lowest limit of detection as well. And we tried in the real sample, in a spike sample of tablets, milk, and wastewater, and we get also the good recovery for this. So we continue this work for another applications or another antibiotics and another pharmaceutical products later with Professor Kondo. Okay, so the second, if we try for artificial sweetener sensor, we see now we know already that artificial sweetener already used in many products like soft drink, for example, and many foods products as well. But the consumptions of high consumption of artificial sweetener could promote the weight gain, brain tumors, cancer, and many other health hazards. And mostly in the soft drink, the artificial sweetener used is aspartame, around 58.3% aspartame is used as artificial sweetener in soft drink. So that's why we want to make a sensor of this artificial sweetener as well. like this, and we use the burned up diamond nano powder and modified also. We make a composite with zinc oxide because it's cheaper, and also we can make it with a simple preparation as well. And we got the result like this. So this is some modifications, and we tried in the cell with 5 milliliter electrochemical cell, and we got the higher signal per background as well. As you can see here, the SPM EDX image. We could find the zinc particle and carbon and oxygen also already modified on the surface of a screen printed electrode. So it means the zinc nanoparticle composite with burned up nanopowder already modified on the surface of SPE or screen printed electrode. And the next we are working, and this is the result here. You can see the different concentration, and we have a limit of detections, very low limit of detection, about 0.07 compared if we use only burned up diamond nanopowder. So after compositing with the zinc oxide nanoparticles, it got a higher sensitivity and a lower limit of detection as well, and a better percent of RSD. And we try in the samples of soft drink sample, namely here, maybe you already know this in Indonesia, we got also a good percent recovery for this. Okay, and this is we compare with the previous works as well. Compared to the previous work, we got a better limit of detections for this work. And the next one, I would like to talk about CO2 electrochemical reductions. Why BDD electrode is good for CO2 electrochemical reductions? Because as we know that the CO2 reductions need a high over potential to reduce to the useful products. So usually to reduce CO2 to CO2 anion radical, it's use the potential about minus 1.9. So it's very high actually. So we use this one because BDD has a long potential window, so that's why it could lower the hydrogen productions. This hydrogen evolution or hydrogen production usually become a competitor for CO2 reductions. So it has a high durability for a long-term reduction process. It can use for practical applications. And we make a review article also with Einaga Sensei about metal modified carbon-based electrode for CO2 electrochemical reductions. And this is my works when I'm doing a PhD under Professor Ainaga's supervisions. I don't know, maybe Professor Ainaga already talked about this, because I'm sorry I didn't join from the beginning because I still have a class in the morning. About this, we could produce CO2 reductions to methanol with a potential at the potential minus 1.3, we got 24% efficiency of methanol, and it's also stable before and after CO2 reductions. No change in PDD surface, so it's good. And actually, we're asking about how to decrease the potential reductions and how to produce higher carbon containing compound, for example, like how to produce ethanol, how to produce acetone, how to produce many other higher carbon containing compound from the CO2. So we try to modify the BDD surface with some metals, because some metals already tried for CO2 reduction actually. For example, like this metal, can see in periodic table here, the yellow one could produce formate, and the blue one is the exceptions, which is a copper. If we try CO2 reductions on the surface of copper, it can produce hydrocarbon and some oxygenated species as well. So that's why we will try to modify some nanoparticles, some metal nanoparticles on the surface of BDD. So the first of my works with Einaga Sensei at that time, we tried to modify copper nanoparticles on the surface of BDD electrode, and the result at the potential -1, we could find not so much, around 40% efficiency of ethanol, and the smaller efficiency we can find acetaldehyde and also acetone. So it's good, and we continue this work by using another metal nanoparticles. So we use palladium at that time. So the target is we want to find a higher carbon containing compound or to decrease the potential reductions of CO2. So usually if we have a CO2 reductions on the surface of PDD electrode, usually higher potential, more than potential 2, we can reduce CO2, but then we try to reduce that potential. So we try to modify it with palladium, and we could decrease the potential reduction until minus 1.6 volt, and we get the product of CO and also formate. And also we produced 2 articles for this. Actually, the first is one, and the second we try with the different concentrations of our for example, in our electrolyte, for example, like NaCl and also KCl, is suggested to use as an electrolyte also with the higher concentrations. For example, like in 1 mole. So we can get the higher concentrations or high efficiency of formate in this. And continue this work also. This is the works with Professor Evandini and Professor Ainaga. So we modified with iridium dioxide on the surface of the PDD, and also we get the product of formic acid at that time at the potential minus 1.7. Okay, so this is our recent works in Universitas Airlangga. So we continue to work with CO2 reductions using MAXEN or Ti3C2TX with the collaborations with Dr. Khaja from ITB or Institute Technology Bandung. So we modified on the surface of boron diamond electrode. And then we use a various concentration of MAXEN, actually 0.5, 1, and 2 milligram per milliliter. And from this, we can get the result that formic acid also produced with a higher amount if we use the higher MAXEN concentration modified on PDD electrode. Okay, so I think that's all that I can talk this morning. So thank you for all the collaborators and the supervision by Professor Ainaga and Professor Evandini, and also we're just starting collaborating also with Professor Kondo, and all the grants, including LPDP scholarship grants that I can get from master and PhD degree, and other grants, research grant that I got from Universitas Airlangga and national and international grants as well. And this is my groups, actually a very new groups, nanoalchemistry research group, and also I belong to nanotechnology and nanomedicine research group in Universitas Airlangga. So that's all. Thank you very much.
Thank you, Dr. Prastika, for your kind lecture. That's definitely interesting. Is there any question from the audience? You may use the raise hand feature or type your question in the chat box, which is also okay. Any questions? Hello. So nobody asked any questions yet. Wait. Okay. Oh, okay. Here we go. Oh, actually, this is also the presentation for the presenter for today, Dr. Irkam.
Yeah.
Go ahead. Thank you.
I took the opportunity because
Right.
because this is a very nice opportunity to asking some interesting seminars that is also presented by Dr. Prastika. So thank you very much, Dr. Prastika, for the talk. I want to briefly ask you about the modification of the metals for the CO2 reduction. So when we are more, I saw that you write a review about the modification of BDD for the CO2 reduction. So what is since what is the benefits of the use of the BDD itself for the, I mean, compared to, for example, if we are using glassy carbon, for example, for the CO2 reduction. So, and then we modified it with the metals, the same metal. So what is the benefits of using the BDD as the substrate of the modification?
Sorry. Okay. Thank you very much, Dr. Irham, for the questions. Okay. The first thing is that boron diamond electrode has a higher stability compared to glassy carbon. That's the first thing. So if we make for a long time reductions, it has a better result actually compared to the glassy carbon. So I have a result about that, but I think I don't have in this slide. So we tried with boron diamond, also glassy carbon, and we modified with the metal nanoparticles. At that time, it's a copper nanoparticles, and we try within copper modified on the glassy carbon electrode couldn't produce C2 and C3 species at the time. So if we modified on the surface of the PDD, we could get the product. Maybe the main reasons, the first reasons, I think, because BDD has a longer potential window compared to glassy carbon is very shorter. So that's why the hydrogen production is higher at the surface of a glassy carbon electrode. And the hydrogen evolution is the first thing that we ignore in CO2 reductions. So that's why we use the BDD compared to the glassy carbon electrode. BDD has that better behavior actually for CO2 reductions.
I see. Thank you very much. Yeah,
thank you.
Thank you very much.
Thank you. Yeah.
Thank you, Dr. Irham. So if there's no other question, I think I might have a question, which is about the artificial sweetener sensor. In this might be a kind of like a stupid question, but in what scenario is the artificial sweetener sensor used? Like in, I mean, our daily life, or is there any specific application that you have in mind?
Yeah, actually, we can have it in a daily life. For example, if we want to know like the concentrations of artificial sweetener in soft drink or in food, for example, if we don't know what is it, for example, we can make that for sensing in the soft drink or any other foods. So we have collaborated with ITB and also Universitas Gadjah Mada, as well, and IPB University as well for this works actually. Yeah, so we make an electrochemical sensor, which is in Universitas Erlangga, and other colorimetric sensor in Universitas Gadjah Mada, in IDB, and also IPB. Yeah, like that.
I see. Okay. Yeah, that's definitely interesting. So, okay, one more chance. If there's any questions from the audience. 1, 2, 3. No. Okay. Okay. So there seems to be no further questions from the audience. So let me summarize a little bit. So Dr. Prastika is working on antibiotic sensors as well as artificial sweetener sensors, where antibiotics, if it is used in animals and when they are consumed by humans, it would lead to several health problems such as heart problem or bacterial resistance. Which is why this antibiotic sensor is really, really important. And she also has extensively explained about the carbon dioxide electrochemical reduction. So thank you very much, Dr. Prastika, for your time.
Thank you very much for the invitations. I hope that the results of boron diamond also will develop in Indonesia for the next. Yeah, thank you very much. Thank you.
Thank you very much. Okay, so let's have a round of applause for Dr. Prastika. Okay, and before we move on to the next presenter, I would like to also remind everybody that hasn't done this already to fill the Google form so that you can claim your certificate for participating in this webinar. Okay, so our last speaker for today is Dr. Irham from Pajajaran University. So before I give the floor to him, I'd like to introduce him to you guys. He got his bachelor degree from the Department of Chemistry, Universitas Indonesia, and he got his master's and doctorate degree from the Department of Chemistry in Keio University, Japan. He also has many published works. Two of those are detection of dissolved hydrogen in water using platinum modified boron doped diamond electrodes, which was published in Journal of Electroanalytical Chemistry in 2022. And then another one is the simultaneous electrochemical detection of ozone and free chlorine with a boron doped diamond electrode, which was published in Analyst in 2022 also. So his presentation will be about boron-doped diamond electrodes for chemiluminescence sensor. So before I give the floor to Dr. Irham, I would like to remind everyone that we will have 30 minutes of this session also, including the short Q&A session at the end. So yeah, I think that's all my introduction. Let's welcome Dr. Irham to give his presentation.
Okay, could you hear my voice? And
yes, yes.
Is my slide could be seen by the audience?
Yes, we can see it.
Okay. Okay, thank you very much for the introduction for the Mrs. Moderator. Good morning, everyone. Good morning, ladies and gentlemen. My name is, my name is Irham, as been introduced by the moderator that I'm from Department of Chemistry, Universitas Pajajaran, Pajajaran University. I'm, as also already mentioned by the moderator, that I'm previously a student in University of Indonesia, which is a Professor Ifandini student. And after that, I do my PhD, my master and PhD in Keio University with Professor Reinaga. So as he also mentioned that this is a very nice seminar because this is like a family gathering for us because the speaker is all my professor and also Kondo Sensei and also my friend Prastika. And I would like to thank you especially for Dr. Nita, which is also my friend, our friends, for the invitation for this beautiful seminar. So I would like to start my presentation about the electro-generated chemiluminescence, or we short it as ECL, at boron-doped diamond electrode. So I would like to claim first that the data that I present here is actually work done in Einaga laboratory in Japan, in Keio University. So because I still could not set up a new ECL instrumentation in University of Pajajaran. So I hope in the near future I can do more about the ECL again. And since I'm a very new lecturer in Universitas Pajajaran, so I don't have any new result for the BDDs yet in here. Now it's on progress. So let me start that about introduction of the ECL. So Professor Ifandini already briefly mentioned about the ECL, which is a phenomenon where the light emission at the electrodes in electrochemical cell caused by an energetic electron transfer or redox reaction, which generate an electrogenerated species in the solution. So the step is first is the electrochemistry, and then a chemical electron transfers, and then a luminescence process. This is sounds complicated, but it's actually not so much because it's generally just the same as normal electrochemistry, but instead of we are observing the signal of the current that everybody already talked about, but in this time we are observing not only the current, but also more importantly is the light or the luminescence produced at the surface of the electrode, especially BDD electrode that we will talk. So this is a simple mechanism that there are usually two kinds of chemicals needed to make an efficient ECL process. First is a luminophore, and the second is an coreactant, or we call it coreactant, or a sacrificial chemicals that needed for the luminophore to generate luminescence or generate light. And when we are see the data, when we are combining the data from the current and from the observation of the light, we can see here that when the oxidation is start at the current, which is the black line, the light is also starting to be observed. But the light observed here is much more sharper compared to the current. So this is one of the benefits of using electro-generated chemiluminescence, because we can have an even better signal and more sensitive signal compared to normal electrochemistry, even though electrochemistry is already very, very nice method. So a little bit complexity, but we can increase some of the sensitivity, especially in the application of biochemistry. So to give you a better insight of what happened in the ECL process, so here we can see that the I can maybe repeat. We can see here that when the current start to increase in the electrochemistry, we can see a light generated in the surface of the electrode. So this bright light is the one that we are observing using a photomultiplier tube or a light sensor that usually placed on the top of the surface. So we can observe simultaneously between the current signal and the light signal of the chemiluminescence. So I mentioned that we usually need two kind of chemical in the we need two kind of chemical, which is a luminophore and a coreactant. Luminophore is the light source of the luminescence, and the coreactant is the helper that to generate the light itself. Usually a very strong oxidant or very strong reductant, because it's need a high energy transfer from the luminophore to generate chemiluminescence. And the most used luminophore is tris-bipyridine ruthenium, or we call it TPA or TPRA. And the second one is luminol. You already know that luminol is a very famous use in the chemiluminescence. Usually we use it for a criminal scene. Maybe if you like a police drama or something, that people checking the blood evidence using luminescence of luminol. And the coreactant is used, I'm sorry, this is ruthenium. I'm sorry. The left one is ruthenium, and the TPA or TPRA is the coreactant itself, the tripropylamine, which is the most used coreactant in the ECL process. And this is the only couple that I will mention later also, the only coreactant that used for commercially available ECL technique. But other coreactant, of course, is also being provided. The example that I will mention here will be a peroxydisulfate and a hydrogen peroxide. So what is the ECL usually used? The application of the ECL is usually for biosensor, kind of biosensor. So here, for example, is for detecting an antigen, DNA, hormones, or drugs, or more recently, the famous one is SARS-CoV. This is the concept of the typical ECL biosensor. So first we catch the analyte that we want to see using an antibody, which is the one antibody is fixed on the magnetic beads. The other one is fixed with the ruthenium to give the signal. So the more analyte is captured by this antibody, the more light will be also generated. So we can see in the result, we can expect a higher ECL intensity when the higher analyte is happen. So this is a normal biosensor, but instead of observing other things, we observe the light that is marked by the ruthenium and generated with the help of TPRA. So the advantage of ECL is high sensitivity. So compared to other biosensor that usually used for immunoassay, such as ELISA or surface plasmon resonance, the LOD of the ECL is very, very small, which is very nice to detect small things, usually for viruses and everything. The emission can be controlled also, because the emission of the light will be only happen when you apply a potential. So this is the only coreactant couple that is commercialized by two big companies, which is one is the Hitachi High-Tech in Japan, and the other one is Roche Roche or Rose, I don't know, which is an American company. But the couple is only ruthenium and tripropylamine. This is the image of the device from the Rose. This is the schematic representation of the commercialization system. So first we catch the analyte by adding the antibody in the one sample tube, and then we put the magnetics, because the beads have a magnetic part, that when we are applying the magnetics below the electrode, everything will be in the front of the surface of the electrode. Then after everything is lining on the surface of the electrode, we can generate the light by applying potential, and we observe the light itself by a PMT. So usually the both company that I mentioned, which is Hitachi and Roche, usually use a conventional electrode material. This is where the topic getting interesting, because we are in the BDD seminar. In Hitachi, they are usually using a platinum electrode, but the platinum electrode, despite of its excellent stability, I mean, not as excellent as BDD, as maybe you already get, but the ECL intensity is quite low because it's less attracting the TP array. The diffusion of the TP array is not so good. But in the other hand, the carbon electrode, which is mainly used by Roche, is limited one-time use. So you just use it and then throw away, use it and then throw away, despite of its higher ECL intensity. But boron doped diamond or BDD electrode, with its beautiful advantage compared to the conventional electrode that I think you already saw these things maybe 5 times already in this today, with the beautiful of advantage that BDD, despite of being a carbon-based electrode, which attract the TP array more, diffuse of the TP array more, but it also have a higher stability like a metal electrode, even better than metal electrodes, because it's a diamond compound, which is, we know, very, very stable and very, very inert. And I want to mention about one of the biggest advantage of the BDD in the ECL application, which is the stabilization of highly active species. As I mentioned, that we usually use a very active species to help generating the light for the luminophore. But because of the BDD have a very unique property of stabilization of highly active species, we can expect a more stable generation of ECL of the electrode. So we expect that, and we already get the result, that the BDD is better than platinum and carbon electrode. So here's our most recent ECL's publication, which is done by Mr. Sakanoue, my junior and Professor Ainaga's students. We are comparing the most used ECL system, which is ruthenium TP array, in using a BDD with this mechanism. So there are 3 steps. First, that I mentioned already. First, the generation of the radical, oxidation, and then reaction, and then we generate the luminescence. So in this case, we use 2 kind of surface termination. So this is also one of the beautiful things of BDD. We can control many of its parameters. For example, if we compare to platinum, we can only use platinum. Maybe we can try to different crystal size and everything, but usually platinum is a flat surface. But BDD have a very unique, we can control many unique properties of the BDD, and one of them is surface termination. And other things is also already mentioned by Dr. Prastika, is the boron concentration. So depends on our preparation of the diamond, we can have a different behavior, which is one of the interesting part of using a diamond. So here we are controlling the surface termination. One is the oxidized one, and the other one is the cathodic, is the reduced one. The reduced one is usually we call CRBDD, while the oxidized one we usually call AOBDD. And if we can see here that CRBDD having a higher ECL intensity compared to AOBDD. And this is due to the hydrogen termination facilitate the TP array oxidation. As I mentioned, that the oxidation of the TP array is one of the first step and very important. And BDD in its termination, they have more diffuse. The TP array diffuse more to the electrode, which also help to generate more light. we are using impedance to confirm that. And compared to the platinum electrode, here we only showed you the platinum because usually carbon electrode is used only one time. So we want to also emphasize on the stability of the BDD itself. So compared to the stable platinum electrode, BDD have 70% enhanced ECL emission compared to PT electrode, because it's already mentioned before in the other journal that surface oxidation of the platinum is decreasing TP area oxidation, while BDD can maintain a stable TP area oxidation. So in here we can propose that in the normal or commercialized system for the ECL, we can say that BDD could replace a conventional platinum electrode, which is very, very interesting. So that's about the TP area technique, but we also, Einaga Sensei also mentioned that the ECL is one of the fundamental studies. So we also try to see a new ECL system that can be used by only BDD electrode. So this one is one of the other candidate of ECL couple, which is using a peroxydisulfate. It's already known that peroxydisulfate could help also ruthenium to generate ECL. And in the BDD, we can see that compared to the conventional glassy carbon and platinum using peroxydisulfate and TP array, we can see only BDD give us signal in pure aqueous solution. It's needed to be concerned that it's a pure aqueous solution. So if glassy carbon and platinum also possible to generate this kind of signal, but in the pure aqueous solution, it's quite hard because BDD have higher wide potential. BDD have a wider potential window that is beneficial for this kind of technique because it's generate the light at a quite negative potential of -1.7. It's similar to what Prastika, Dr. Prastika and Professor Ifandini, Professor Kondo, and Professor Inaga said. But this one is my main topic on my PhD study, which is the unique electrochemical reaction at BDD. So I mentioned before that we need two kind of thing, which is one luminophore and the other one is coreactant. The coreactant need to be a very active species, such as a peroxydisulfate or maybe hydrogen peroxide. But interestingly, BDD is already reported to be able to in situ generate it from a very more stable or less reactive compounds such as sulfate and carbonate. So we don't need to put the highly reactive compound. We just put sulfate, which is also used as electrolyte, and we produce the active compound of the coreactant so that we can generate ECL without the needs of putting the coreactant itself. This is only can be done by BDD, just to mention more. So the peroxydisulfate here is generated in the front of the electrode, and with only sulfate electrolyte and carbonate electrolyte, we can have the ECL signal. And of course, we're adding the luminophore, but with only luminophore and electrolyte, we can generate the signal. This is very, very beneficial because adding the reactive compound or adding the coreactant is first give you a cost. Second is quite toxic because it's a reactive compound, and usually you provide radicals and everything, which is quite troublesome to be managed. And we also following the green chemistry rule here because we decrease the use of chemicals and it's hierarchy chemicals. So this is a very interesting future for the ECL using the BDD electrode. And we compare both systems, that carbonate system using both sulfate and carbonate, and we see that carbonate system could be activated in lower potential. So if you want to do it more lower potential, which is also maybe less electricity that you pay, maybe carbonate is slightly better compared to sulfate. Last one, which is also already mentioned by Professor Ivandini, this is also, we also work on the luminol and hydrogen peroxide system, where luminol is used as luminol and hydrogen peroxide is a co-reactant. So usually the luminol is become more advantage compared ruthenium, because luminol is cheaper luminophore compared to the ruthenium complex, because the ruthenium complex is quite costly. But the luminol is also have more some disadvantage because of its organic stability. But the luminol is also a very great candidate because it have higher ECL intensity compared to the ruthenium. So anyway, we still need a better alternative because we still need to put hydrogen peroxide usually. But as I mentioned before, that we can generate the hydrogen peroxide also in the surface of the electrode. So we can see here that this is the luminol light, which is blue. So we can see here that using only luminol and a carbonate compound, which is also used as an electrolyte, we can have a very promising result. A very high ECL intensity and a very linear intensity with the carbonate concentration with the chronoamperometry setup like this. This is also already published in 2021, and the other report is also already published in around 2016 to 2022 from Keio University, of course. So I just want to conclude that BDD shows a better performance in the most used ECL system, which is the ruthenium TP array, for immunoassay application compared to the conventional electrode. So we can expect in the future, if we can already mass produce the BDD, we can expect that BDD could replace the system itself. Furthermore, in ECL co-reactant system, BDD also shows other co-reactant system. BDD also show better performance compared to other conventional electrode such as GC and platinum. And lastly, the most unique part is thanks to the BDD's ability to promote unique reactions such as generation of strong oxidant, we managed to establish a novel co-reactant-free ECL system by supplying the in situ co-reactant from the electrolyte. So this is a very, very interesting topic that also get much attention nowadays. And especially because of also the COVID situation. So an ECL is one of the best answer to detect the COVID. So maybe we can expect that BDD's future also might be bright. And as Dr. Prastika mentioned, and Professor Ivandini mentioned, that especially in Indonesia, the BDD is still not used quite a lot. So this is a very good chance for us to develop BDD's electrode in Indonesia, of course, with the help of our Professor Einaga and Dr. Kondo for his collaborations. We want to thank them so much about this. So that concludes my presentation. This is my last photo in the Einaga's group in 2021. This is Dr. Nita here, still PhD student back then. And this is one of my boss, my senior, Andrea Fiorani from Italy. He is the one that mainly developing the ECL in our group. So I'm his student also. And this is my junior, Mr. Sakanoue, that also doing the much interesting BDD's ECL system. So that's all. Thank you very much for your kind attention. I give it back to the moderator.
Thank you very much, Dr. Ikram, for your kind presentation. It was very illuminating. Let me say on the nose there. Okay. Is there any questions from the audience? This is your last chance to ask questions. Is there any questions at all for our kind speaker?
Can I ask questions?
Oh, yeah, sure.
Because it is
course.
very illuminating. Okay, okay, Dr. Irham, thank you very much for your nice works, nice presentations. What about, first of all, BDD? Why BDD only show the signal of ECL rather than other electrodes? That's the first thing. And can you propose which kind of luminophore and how to say co-reactant it's best for ECL system? I think that. Thank you.
Okay, can I answer it directly?
Yeah, sure. Go ahead.
Okay, thank you very much for the question, Dr. Prastika. The reason that only BDD in the normal, in this, for example, ruthenium persulfate, the only BDD can show the signals is because the hydrogen evolution. So same with the CO2 reduction. So because other electrode will have an hydrogen evolution on the negative, on the negative part, I think the hydrogen evolution first will competition with our reaction here. Second, that the bubbles that is generated, because a very much bubble that generated on the surface, it will be hindrance to the light emission. So the detector cannot see the light because of so many bubbles that is generated in the surface of the electrode. So same as the in situ correctant generation, because the wide potential window of the BDD, so in the oxidation part especially, we can oxidize a stable compound such as sulfate into the reactive peroxide sulfate. So both of them is because of the wide potential window. And the second one is also because of the stabilization of the active species, because BDD is strangely, this is still debatable because nobody has still, I think, understand why BDD could make a stabilization of the highly active species. But thanks to that, the reactive species that used for DCL is become stable, and we can expect more generation of light because of that stability. And the second question is about the couple, luminophore correctant couple. So actually there's so many reports already published about new luminophore and new correctant. They are designing so many things, but nowadays still the best one to be used for immunoassay is the luminophore of ruthenium and correctant TP array because of the stability and the high intensity. But actually, luminol having even higher intensity in the same concentration, for example, with the ruthenium, it's much higher. And hydrogen peroxide is also much more easier to access. So actually, if it's possible, luminol and hydrogen peroxide is, I think, is better. But nowadays, still, nothing can beat the ruthenium and tripropilamine. I hope that one day BDD could help generating new one.
Yeah. Okay. Thank you very much, Dr. Rehan. It's interesting. Let's develop BDD in Indonesia.
Yes.
Yeah.
Of course.
Okay.
Thank you very much
Thank
for the
you.
question.
Thank you. Yeah.
Thank you. Is there any other question from the audience? No? Okay. So I would ask questions, but this is definitely out of my comfort zone to be asking questions because it's like very different from what I do. But if I may ask another stupid question, how long do you think for this technology to be even possible for mass produced, especially in Indonesia? And like what factor do you think would help accelerate it?
Yeah, thank you very much. So in my philosophy, there's no stupid question, only stupid answer. So I hope my answer is not stupid enough. So this question might be better be answered by Professor Einaga or maybe Professor Ifandini, since me and Dr. Prastika and Dr. Nita just come back from Japan in several years. But yeah, in my opinion, the one of the things that we need to think about is the mass production of the BDD itself, because making the BDD, as already mentioned by other speakers, including Professor Einaga and Dr. Kondo and Professor Ifandini, is using a very specific plasma technique or filament technique. It's still quite costly, and I don't know, but the technology itself is maybe not as easy as, for example, making a platinum electrode that is much more easier. So the development of economical, viable BDDs production is I think the bottleneck of this. But I think Professor Einaga already done a lot of collaboration with many companies to develop a better economically stable BDDs production. So we hope maybe if it's already fixed, we can maybe make a industry in Indonesia to make BDD.
Right. Accelerated ourselves. Yeah. Okay.
I'm waiting Irham's Corporation of BDD.
we will make it in Kalimantan because because everything will move to Kalimantan.
Yeah, I see. Okay,
Definitely. Right. Okay. One last chance for the audience. Is there any question? 1, 2, 3. Oh, okay. All right. So yeah, thank you, Dr. Irham, for your illuminating presentation.
Yeah, thank you very much for everybody. Thank you, Dr. Pasika, Professor Fandini, everybody.
Yeah, and so let me summarize a little bit. So Dr. Irham is his work is primarily focusing on the observation of the luminescence behavior of the BDD electrode using electrogeneral CL. It gives a stronger chemiluminescence effect, and usually we would use lumina 4 as the light source, and the co-reactants that would be it would be a very active species as a sacrificial helper. This technology can be applied as biosensors with higher sensitivity for antigens, DNA, hormones, drugs, and viruses. And with BDD electrode, the ECL generation is more stable compared to the platinum electrode. And then a BDD can have an in situ generated co-reactant, so it doesn't need to have an added co-reactants in this process, which is beneficial since co-reactants are usually toxic. So yeah, that would conclude our sessions in this second world-class professor series. So thank you again for all our esteemed speakers from Keio University, University of Indonesia, University of Erlangga, and also Pajajaran University. We are honored to have you as the speakers in this series. And thank you again for illuminating us with this topic. So I guess that's it from me. I will give the floor back to our MC, Fikan Mubarak. Thank you.
All right. Thank you, and job well done, Ms. Leah Amalia, for bringing the discussion much more alive. Also, highest appreciation to all the speakers who have delivered points and explanation, enabling us to comprehend more of today's topic. And appreciation for the participants and also invited speakers who have actively asked remarkable questions to strengthen our knowledge. We hope that today's event will bring benefits for us, scientific community, and also for our country. And last, as the token of appreciation, we would like to present certificate of appreciation to first Professor Dr. Yasuaki Einaga. And the second for Associate Professor Takeshi Kondo. The third for Professor Dr. Ifandini. And the fourth certificate for Mrs. Prastika. And then the fifth for Mr. Irham. And also for our excellent moderator today, Mrs. Lia Amalia, STMS. Thank you for the moderator. Before we close our webinar, let us take the last picture of today's event. So please kindly to turn your camera on and give our brightest smile to remember. Maybe operator can lead the photo session. Okay, there's no committee, so I will take the picture, my own. Okay, everybody, cheese. Okay. Then the second slides. Cheese. Okay. And the third slide, cheese. And the fourth. And last for the fifth. Okay. Okay, thank you. Once again, don't forget to fill the attendance. The link is in the chat sections. So this is the end of the second World Class Professor webinar, but don't worry, there will be the next World Class Program webinar on 6 October 2022. So roses are red, violets are blue. This is not the last time I'll ever see you. See you in the next World Class Professor 3 and thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you very much.
Einaga
Thank you very
Sensei, Kondo
much.
Sensei,
Thank
Professor
you, Kondo
Imani,
Sensei.
Dr.
Konnichiwa,
Kondo
Einaga
Sensei.
Sensei.
Thank you so
Kondo
much.
Kondo Sensei,
Sensei.
osashiburi desu.
Irfan. Osashiburi
This
desu.
is a Rioni International webinar.
Yeah.
Sorry.
Okay, bye. See you again.
Bye bye.
Okay, thank you very much.
Thank you, Mbak
Thank you
Nita.
very much. Arigatou
Thank you.
gozaimashita.
Thank you, Nita-san.
Okay.
Welcome to Material and Metallurgical Engineering ITK. I'm Jatmoko Awali, the head of department. I know there must be a lot of questions about what we can do on this study program. Let me get you to take a look at the journey that you can choose to assess your universe. Our strategy to solve these various problems is by dividing our expertise in 4 broad research areas: material simulation and modeling, material manufacture, innovative material, material viral analysis. Let's find out what they are doing.
Material simulation and modeling expertise cover research for modeling and simulating important aspects in material science, including structure, properties, and behavior of materials. Basically, we are trying to construct models and identifying the correct approaches to test theoretical descriptions, experimental observations, or non-experimentable materials phenomena using various computer softwares.
Materials manufacturing studies the processing of materials to improve the efficiency and effectivity of product manufacturing. For example, casting, soldering, carburizing, welding, sintering, polymer extrusion, and composite curing.
Innovative Materials focuses to improve materials by curating and developing innovative composite, metal, polymer, and ceramic, by expanding the design for devices and systems of technological applications such as industrial, medical, and environment.
Material failure can lead to catastrophic accidents like the Titanic, airplane crashes, or collapsing bridges around the globe. The program teaches the student to analyze cracks, corrosion, deformation, and many forms of material failure to find the causes and design the prevention of material failure.
So that is a glimpse of the universe that you can choose. Let's start your journey with us to see more and know more. Because
there is no engineering without materials.
There is no engineering without materials.